Okay, so just as a short introduction, well, this webinar, it's called Novel High Performance Materials and Components. It's, let's say, we are together here representative of different projects from Horizon 2020, from Horizon, yes. So this comes from a topic that was launched by Processes for Planet. Let's say that we are going to go over main hot topics that are being developed in these projects. And the idea is to make it quite flexible. The general picture will be to go ahead with different presentations following the list that appears in the program. And once we finish, or at the end of the presentations, we will have a time for questions and discussion. However, if there is if there is time after finishing one presentation and somebody asks one question and it's time to answer him, we will try to do that. So basically, we have, as I explained you, we have represented in this webinar 6 European projects that are going to contribute with their ongoing activities, their experience to this webinar. We have representatives from HIPERMAT, from ACHIEF, from TOPAM, from ThenWave, from Compass CO2, and from FORCE. Well, to start with the webinar, I will introduce myself. I'm going to coordinate the presentations. I'm Fernando Santos. I'm senior researcher in Fundación AZTERLAN. I'm head of the Special Materials and Processes line. I'm a chemical engineer with around 20 years experience in metal industry as technical manager and 12 years experience in research and development. And in HIPERMAT, I am the coordinator of the project, and I am also collaborating in the design and development of new refractory stainless steel. So I will give the floor to different presenters, and I will just also moderate the questions and answer chapter. Okay, so more things. I think that we will be, let's say, there will be, I think, 20 minutes per presentation. And let's say that I will give the floor. We have not a single presenter for each presentation. There are presentations that will, will be involved two persons. So it will be divided in 2 parts. And as I have told you, yes, please ask any doubt that you may have during the presentation. So without losing time, I will just start sharing the screen because I will start presenting my presentation. Okay. Okay, I think that you can see that it's
yes.
Okay. Well, basically, we are going to go ahead with a new generation of refractory stainless steel from the industry. And we are going to show you which is the effect of cooling rate during solidification on high temperature properties. Well, we are going to go over who we are, who is Fundación AZTERLAN. We are going to give some details of the HIPERMAT project. We are going to introduce the ablation technology. We will go over new refractory stainless steel case study, and we will discuss on the results, basically on mechanical test results and on microstructure analysis. And in the end, we will talk about main conclusions. Well, who is Fundación AZTERLAN? Well, we are a private research center. To give you some details, we are around 1,138 people working here. 17 PhD, actually. We belong to a bigger organization that it's the Basque Research Technology Alliance. We are located in the north of Spain, next to the border with France. We normally generate 15 papers per year. We have 3 spin-offs, more than 2,000 customers, and we have an active surface of 15,000 square meters. Well, our evolution. We started being a testing laboratory in 1974, and we have evolved towards, let's say, a recognized research and development center by the Spanish government. And nowadays we are carrying out different activities, and we are quite active in Europe, and we are, let's say, performing different European projects. Which are the most demanding sectors? We have quite a, let's say, an industrial network around us, and we carry out significant activities for different sectors. For example, iron and steel, automotive industry, wind energy, aerospace, oil and gas, urban mobility, railway, shipbuilding industry, machine tool, and infrastructure. We have a laboratory that gives support in all the research and development activities that we carry out. Is certified by different standards that you can see, for automotive, for aeronautic, and mainly as a general testing laboratory. Well, we provide basic and applied research capabilities. Mainly we work on materials. We design and develop new materials. We are experts in different manufacturing processes, and we develop solutions for different, let's say, technological and control, let's say, solutions. We also develop, let's say, transversal solutions for the companies. We develop intelligent manufacturing technologies, mainly ICT tools. We work also quite in depth in terms of sustainability and energy. We try to solve energy and residues problems to, let's say, to metal industry. And we have other minor related areas like corrosion, surface technology, and fracture mechanisms. Well, a quite overview of HIPERMAT project. Well, this project was born next to a specific study case. It's linked with the hot stamping furnaces. These furnaces have tighter requirements. They work at very high temperatures. They have to support significant loads. And let's say the environment is quite corrosive because there are gases inside the furnace. So currently the materials and let's say the elements that are inside the furnace are suffering from different type of failure modes, like thermal fatigue combined with corrosion and creep, and also wear, because they are moving and they are suffering quite a complex, let's say, type of failure modes. Well, the project itself is a combination of solutions. It's supported in advanced design tools and aims at developing new high thermal and corrosion resistant alloys. This is one of the main aim of this topic. We are going to talk about refractory stainless steels. We are also developing high performance alloys in terms of coatings over, let's say, where surfaces that are going to be open or are going to suffer wear. Also, it's critical, the control of the furnaces, and other aspect critical is the development of new embedded sensors by printing them into, let's say, into beams is the current case. Which is the main impact that we aim at having? Well, we are trying to optimize the component manufacturing processes, reducing the use of materials and increasing the efficiency of the plant, reducing less plant shutdowns because of failure of different components. Also by reducing the energy and resource consumption, by more efficient technologies to manufacture the components. Minimization of waste and energy consumption using modeling tools and advanced design of processes and materials, and introduction of protective layers in components, reducing critical elements in bulk materials, and extending the life of these components. Okay, and now we'll go. I will give the floor to Emily Barbarias that will go over the ablation technology. He is senior researcher in Fundación AZTERLAN. He is developing its activities in the aluminum line. He is a mechanical engineer with also 20 years of experience in the metal industry, and he is developing new manufacturing solutions for metallic components, such as ablation, that in the project we call hydrosolidification also. So I will give him the floor. So Emily,
Yes. Thank you, Fernando. Okay, so let's introduce a little bit the ablation technology. So ablation is kind of developed from a casting process. Yeah. So with casting process, we have quite a high flexibility for geometries, etc. And this casting operation is driven by fluids to disassociate the mold and solidify the metal. So the use of fluids produce a strong cooling, and with a strong cooling, we can achieve enhanced mechanical properties. We have here a typical photo that we can find in the internet. Okay, thank you. Okay, here we have 4 pictures about the ablation casting. Yep. And in the left upper left picture, yeah, thank you. We have a sand mold. This sand mold is produced or linked by a binder, and this binder is water soluble. Yeah. And at the upper right picture, we see how water jet is dissolving the sand mold. The sand mold is washed away, and so we are impacting directly the metal inside the cavity. So the cooling is driven by the water jet. And in the lower pictures, we can see the part as it gets out from the mold once it was away, and the part is finished. Okay, by making a short comparison and a little bit of try to put the ideas in clear. In conventional casting, the melt fills the cavity, and during the filling, the melt is losing energy towards the mold. And at the end of the melt filling, we have a skin of the mold that has been heated, and slowly by the thermal coefficient of transfer coefficient, this heat is slowly going towards the rest of the mold. So in the conventional casting, the process is a compromise and about the mold's properties. During the filling of the part, we'd like to have something which is adiabatic, which takes out as less as energy as possible. And in the opposite, once the solidification starts, we would desire kind of a higher degree of heat transfer. So at the end of the day, in casting, we have a kind of compromise about those two processes, and somehow the technology and the parts and the geometry, they are adapting each other. So everybody knows more or less what is a geometry that can be cast or not. Yeah, and we go through those equilibriums. In ablation, there is 1 degree of liberty more, and this is the term that we should keep in mind. So the mold is active during the shaping of the part. So the liquid fills the cavity, is given shape, but the solidification itself is driven by the blue arrows, would represent the water, and this is giving us a higher liberty or control about at what speed we want to cool down. And also it makes the solidification much more directed than in the other cases. Okay, so for me, to put things in clear, ablation is kind of, we have another degree of liberty to play with. Okay. Finally, those are tests that we carry in AZTERLAN, and you can see here a high melting point alloy being cast in the picture 1. Then it's tilted, and when it's rotated, you can see in picture 2 how water spray has dissolved the mold, and we are impacting in the solidification, in the solidifying part. So that's all from my side. Thank you, Fernando.
So now we will keep ahead. So next point is the new refractory stainless steel, the case study. Well, as has been before, there are different, well, the rolling beam is a furnace, is based on a technology where we have different metallic beams supported on rollers with rings. And this equipment works under fluctuating high temperature conditions in the entrance of the furnace. Whereas in the center of the furnace, we have quite a constant temperature, higher than in the entrance. And that makes that under these conditions, failure modes are thermal fatigue of beams at the entrance of the furnace, combined with corrosion and creep at the inside of the furnace, and combined corrosion, creep, and wear of rings. So this is something we have evaluated, which are the main conditions. We are going to go over the beam inside the furnaces that currently represents quite a regular failure mode that generates shutdowns in the plant. And this has been of goal to improve creep mainly and crack growth rate. These are the two main issues that are affecting these beams. So when we have studied the different qualities of different type of alloys that are used in the industry, we have taken as reference the more standard alloy, and we have just studied how the different chemical elements, how the process, and how the phases affect these materials. We have just made a quite complex study supported by different partners, and in the end we have just checked that, well, higher nickel contents improve the properties, and other chemical elements improve them by let's say minor additions like niobium, molybdenum, copper, and wolframium, and tungsten. And also we have checked that why this happens, why it is happening, and this is because of the precipitation of different phases or just the formation of others. So this has been a little bit the way of working on over that. We'll go on the results. Well, the results, as we have explained before, main critical aspects we have considered that are creep and crack growth rate. So we have gone over creep tests. Yes, this is the type of test bars that we have prepared. These are the type of machines that we have used. And we have just compared the results using the Larson-Miller parameter. That it's the equivalence of time of temperature for a steel under a thermally activated creep process of stress rupture, and it permits the calculation of the equivalent types necessary for a stress rupture to occur at different temperatures. If we go over the Larson-Miller graph that we have here, we can see that just to concentrate on the main results, you know, the lower, that it's in red, in the lower side of the graph, it represents the natural cooling of one mold. In blue, you can see the standard values of this alloy, the one 4848, and in red, the achievements that we have got by means of modifying the alloying. For example, the triangle line corresponds to a modification of the water, for example, of the water cooling. It improves significantly the values of the non-water cooling samples, and in, let's say, the square lines represent the new alloy enhanced with the water cooling. So we are achieving, this is a logarithmic representation, significant improvements in creep for this alloy, not only changing the chemical composition, but also modifying the cooling rate. This is quite critical for us. We have also proceeded with the crack growth rate tests. In this case, we have used this type of test sample, where we have generate one, let's say, one small, let's say, crack, I would say, and we have just made this test. We can see very different values. We can see how this, for example, how the reference alloy that it's in natural cooling, it's the red line in all of the graphs that we can see, is significantly lower the behavior in terms of time until rupture. If we compare with the green line, that it's the same alloy but cooled down using the ablation process. And we can see also a very high increase in the properties, just also combining also the chemical composition modification. So we are multiplying by 10 the resistance to let's say to craft growth rate if we just combine chemical modification and also a quick cooling rate by means of water by using the ablation process. We have tried to investigate and to analyze which is the reason for this behavior. So we have gone over the analysis by means of SEM, ADX, of the quantity of primary and secondary carbides, the morphology and chemical composition of carbides, and the segregations in grain boundaries. What we have seen? Well, we have seen that, well, first of all, what we have done is to make a stabilization heat treatment, because we have seen that the condition of the alloy changes with time. If we keep it at 930 degrees for some time, there is a significant precipitation of carbides. So we have carried out this stabilization heat treatment. We have just checked that there are more primary carbides in the gravity casting sample compared with the hydrosolidified sample. The precipitation kinetic of secondary carbides is similar for the two types of samples in the first 20 to 30 minutes. In the case of the hydrosolidified samples, there is a higher percentage of precipitated secondary carbides, and we can see that down in the pictures. We can see how primary carbides, that are the biggest one, are similar in grain boundaries, but secondary carbides, the tiny ones inside the grains, are more homogeneously distributed in the hydrosolidified sample. If we take it into numbers by making an image analysis, we can see how primary carbides, the percentage is higher in the case of gravity casting, whereas secondary carbides is significantly higher in the case of, let's say, hydrosolidified samples. We can see the graphs. Well, if we take a look at the morphology, we can take a look at this morphology in the case of the, let's say, standard cooled down samples in the mold. We can see these blocky type carbides in grain boundaries, whereas the shape of carbides changed completely in the hydrosolidified samples. It looks like a fishbone appearance. They are tiny, and they are better distributed. This is quite significant. The chemical compositions of carbides also is slightly different. We have carbides richer in those elements in chromium, niobium, and tungsten. In those elements, in the case of gravity castings, compared with hydrosolidified samples, this has somehow, well, it makes sense that we have less segregation in the case of hydrosolidified samples. If we take a look at we have made line scan to check which is the segregation. We check that chrome is more segregated in the gravity castings, whereas it's less segregated in the case of hydrosolidified. Carbon also is more segregated in the dendritic spaces in the case of gravity casting. And we have a stabilization time that has no effect on the segregation. So this is what we can see in next pictures. These are the line scans. And what can be seen is that there is lower segregation if we cool down quicker, that in the case that we keep the metal into a mold that cools down slower. So this is the general picture, and we'll go to the conclusions. Well, let's say that hydrosolidification has a significant effect on clean properties, improving them significantly. In both cases, in standard alloy and in new formulated alloys. Also, the chemical composition modification that we have performed has a significant effect on clean properties, and in fact, it affects a lot on creep and on creep growth rate. And microstructure, as we have seen, it's quite remarkable how primary carbides are present in the gravity casting sample in a high quantity comparing with the hydrosolidified samples. The precipitation kinetic of secondary carbides is similar for the two types of samples in the first 30 minutes. In the case of the hydrosolidified samples, there is a higher percentage of precipitated secondary carbides. Also, it's remarkable how the different carbides are richer in those elements of main alloying elements in the case of gravity casting compared with hydrosolidified samples. We can also see how tungsten carbides are more irregular than chrome and iron carbides that are more polygonal, that chrome and carbon are more segregated in the case also of gravity casting, and that the stabilization times has no effect on segregation of the different chemical elements. And from my side, that's all. Start sharing. I think that we are on time. So we will go without further delay again with the next presentation. The next panelist is well, it represents project ACHIEF. It's Andrea Gregores Coto. She's physics. He currently works in AMEN in the development and research area in the artificial intelligence group. Her role is focused in the development of artificial intelligence tools for the discovery of novel materials such as the ACHIEF project. She will present the presentation and will continue with Tom Anderson from BTT. Tom Anderson is working as a senior scientist and researching leader at BTT in integrated computational material engineering team that is focused on modeling the behavior and performance of metallic and ceramic materials. In ACHIEF, he acts as work package leader and participates in developing crystal plasticity model for ESA and chrome steels. So, Andrea, you can share your screen. The floor is yours.
Okay, thanks a lot. Well, hello to everybody. I'm going to talk about the discovery of new materials such as, well, in this particular case, concretely high entropy alloys in the scope of the ACHIEF project. I'm going to talk about part of the artificial intelligence where we have that we have used to generate new synthetic candidates to be possible high entropy alloys. And then Tom is going to talk about the simulation part where we have chosen a high entropy candidate to be experimentally synthesized. Well, first of all, I'm going to focus on the high entropy alloys concept. While a conventional alloy has one principal chemical element and then a fewer concentration of the other elements, a high entropy alloy has multi-principal chemical elements in similar proportions, as you can see in the figure. Apart from this, high entropy alloys can appear in different phases, such as the solid solution 1, intermetallic, amorphous, or a mix of them. And depending on the final phase, they will present different final properties. Due to the presence of these multi-principal chemical elements in the high entropy alloys, this gives rise to a high entropy, which is computed with this formula. So this is important for the concept of Gibbs energy, which is related to the stability of a system. So the higher the entropy it is, the more stable will be the system. So that's really important for the stability. This entropy is really important for the stability of the final alloy and also for the its configuration. Just to make a little bit more clear, in this graph we can see that for values bigger than this one, we can consider an alloy to be a high entropy one. High entropy alloys are of great interest for some industrial applications, such as in aeronautics, because of their strength, superior hardness. Well, they have really interesting properties. But because of the fact that they can present multi-principal chemical elements, this gives rise to a lot of possible combinations. So to discover a new high entropy alloy is really difficult because of this reason. Of course, experimentally, it's really hard to deal with this amount of possible combinations to check them, and computationally it's really costly. So one of the motivations of this ACHIEF project is to use artificial intelligence in order to accelerate this process, the process of discovering new high entropy alloys. So the methodology was as follows. First of all, a dataset was created based on literature. Once this dataset was finished, it was used to feed the neural network. And we have trained the neural network with this dataset. Once the neural network is correctly trained, it was able to generate some candidates to be possible high entropy alloys. But in order to check if they could accomplish the properties of these concrete alloys, a validation method was developed. And in this case, we have made use of these databases, which are based on density functional theory, to check if they had the properties to be high entropy alloys. Concretely, focusing on the first step, the dataset, it ended with more or less 1,000 high entropy alloys, which were found in literature. And each alloy has related 15 physical features that describe its behavior. Then a column with the number of elements that contains each alloy. Its general phase, which, as I have said before, it can be solid solution, in organometallic, amorphous, or a mix of them. In the particular case of the solid solution ones, its specific solid solution phase was also specified, which could be, for example, FCC or PCC structure. And finally, 78 chemical elements were taken into consideration to be part of the final alloys. So they were included with their corresponding concentration for each alloy. About these 15 features that describe the physical behavior of the high entropy alloys, they are here included with their formula and also with their description. Of course, as I told before, entropy is really important for the stability of the high entropy alloys and configuration, so of course it's included. The sign for the enthalpy, which is related to the Gibbs energy, and then also its standard deviation. Then we have included the mean atomic radius, the atomic size difference, the electronegativity and its deviation, the valence electron concentration of the alloys and its deviation as well, and then some mechanical parameters such as the mean bulk modulus and its standard deviation, the Young modulus, and the Shears modulus. And finally, the average melting temperature and its deviation as well, because this is an important parameter for the final properties of the alloy, depending on the applications that they want them for. So once the data set was developed, well, it was well structured, pre-processed, everything is okay, it's ready to be used. So the next step was the neural network. In this particular case, we wanted to generate new synthetic candidates, so we have made use of generative adversarial networks, which are a kind of networks that contain at the same time two networks inside, the generator one and the discriminator one. And this works as follows. First, the generator is fed with the data set with the real samples and a noise. So with this, it is able to generate some synthetic samples, which are used to be input for the discriminator. So then the discriminator compares these synthetic samples with the real ones and determines if they are real, what it means if they are similar to the real ones in the distributions that follows, or fake, if they are really different. So the discriminator helps, this works as a loop where the discriminator helps the generator to calibrate its weights in each iteration. So in each iteration, at the same time, the generator is improving the generation of better candidates. So once the neural network is correctly trained, the discriminator will not be able to distinguish between the dataset and the generated samples. So in this particular case, we have used a specific kind of generative adversarial network, which is the conditional tabular GAN. And that's because the kind of data that is contained in our dataset. Like we have discrete and continuous data. This is really, it was really good for the treatment of this data. And also with this kind of neural networks, we can make use of non-Gaussian distributions, mixed data types. So as you can see, because of the kind of data set that we have, this was a really good option. Once the neural network was correctly trained, we have been able to generate some candidates. So here comes the validation part, where we have to check if they are possible high entropy alloys or not. Well, the first good evidence was that we have found, well, the neural network has generated this compound, which was not included in the training dataset. And it has predicted a phase that it was the amorphous one. Then this same compound was found in literature in this paper with experimentally proven phase to be amorphous. So this is a really good evidence that the neural network is correctly trained and that the compounds could be possible high entropy alloys. Then we have also made use of the Open Quantum Materials database to make a comparison of the values of the enthalpy. So first of all, we have checked it for the real compounds, and we have compared the value of the enthalpy given by the dataset and the one computed by this database. And as you can see, they are in really good agreement. So we have determined that this is would be a good way to validate also the generated compounds. So we have made the same for the synthetic compounds generated by our neural network. And as you can see, the value given by the neural network and the one computed is also really accurate. So this is another good evidence of the correct that well, the neural network is generating good candidates. Once this process was ended, we have introduced all this information in a software tool with an interface to generate a high entropy alloys. So here's a tool where you can choose the kind of material you want. In this case, we're only going to focus on the high entropy alloys. And then, well, you can choose the number of samples you want. You can generate them, and you will have it in an Excel file, the new compounds. Or you can also apply some screenings, like number of elements and melting temperature range, and you will have it in another Excel file. Finally, in order to send our data to VTT for the simulation part, where the final high entropy alloy will be chosen, we have done a screening part in terms of, well, to make it easier for them to analyze, just not to send a lot of data. So first of all, the first approach was to take into account, as I mentioned before, 78 chemical elements, where we have removed noble gases and radioactive elements. But then we have done another screening. So we have removed also the rare earth elements, the toxic ones, expensive ones, just in order to not make it dangerous when manipulating them in the laboratory, and also because of costs. And then we have also removed elements with a melting temperature higher than 2000 Celsius degrees, because it is also difficult to deal with them in the laboratory. So finally, we have ended with 19 chemical elements to be possible parts of the high entropy alloys. Just some numbers, as you can see, taking into account only 19 elements, if you, for example, want a high entropy alloy of 5, 6, 7, or 8 elements, you will have these huge, these large numbers. But these numbers will be bigger because if you take into consideration the possible stoichiometry, it is you have more combinations. So as you can see, it's a huge amount. So finally, following VTT's experience on stability analysis, we have promoted compounds that contain nickel, silicon, or aluminum, because these three compounds are really important for the presence of the gamma prime phase, which is one really important for the stability of the final compound. But always taking into account not only for these elements, for all the elements present in the final alloy, that each element were in the desired region. So the desired region is the one which goes between the 5 and 35% of percentage per chemical element. And that's everything from our side. Now it's turn to Torm. Thanks a lot.
Okay, thanks. So I will share my screen here. So following Ayman's neural network analysis, so we'll continue with the selection of the most promising alloys. So the actual use case here is this kind of a steel mill roll component, and the temperatures for that in the operation are up to 1200 degrees or almost to 1200 degrees. So we need to have this kind of high temperature alloy, and due to the schedule of this project, we only had chance to manufacture one alloy, so we had to be quite sure that that alloy actually will be usable in these kind of high temperature applications. So we used ThermoCalc to evaluate these neural network results, and the database that we used was this high entropy alloy database number 4. But some of the elements that were remained in the neural network were missing from this database, so we had to modify those alloys a bit or then neglect some of the alloys. So that was one thing, and also we used this ThermoCalc to verify the solidus or liquidus temperatures for the alloys. So in some cases these alloy temperatures differed a bit from the design parameter used in the neural network. And also in the end, the phase equilibrium diagrams were quite messy for some of the alloys, so those were basically neglected. So basically we first screened this, or did the screening based on this liquidus or solidus temperatures, and took only the alloys that were ThermoCalc predicted to be around or above 1200 degrees, hopefully above 1500 degrees, so it would still have some mechanical strength left in the 1200 degrees temperature, use temperature. And also we took these few elements that are usually used only as minor alloys, so that amount of those wouldn't exceed 5% in the final alloy. And also we further neglected or took this cobalt out since it's quite expensive and might cause some health issues. And well, as said, some of the candidate alloys we had to modify them a bit because there were some of the elements missing from the database. So finally we came up with few possible solutions and ended up with this kind of a 4-phase component. So this was one of those that we did minor modification for those. And for this, it seems to be still usable in this 1200 degrees using operational temperature, and it seems to possess this kind of a dual phase structure. And actually, we found a bit similar alloy from the literature, and at least according to that, the strength and the strain elongations were pretty good. So that's why we are quite sure that this could be a good alloy for the actual use case. So we aim for this with this heat treatment. We aim this gamma prime plus this BCC B2 structure. So this 4-phase structure that should, at least according to literature, be quite good or should have quite good strength and elongation properties. So that was first, and then when we have the microstructure ready, this is the plan to do this crystal plasticity analysis for it. So basically we have done this alloy design, and then the next phase is this actual atomization of the that candidate alloy that has been done already, and it's currently under characterization. So when we have the microstructure and the predicted deformation mechanisms, we apply this crystal plasticity model to get the behavior and ultimately the material performance of the material. So here is the example of how we are going to do that microstructure of that. So basically we have the characterization data, we take the orientation distribution from that and create this synthetic representative volume element. So this kind of representative material block that has the same orientation distribution as the real material. And we use that for this crystal plasticity analysis. So basically what we can do is to see some trends, how this temperature would affect it, and also the grain size, and among other things. So those are the most important parameters in this case. And here's an example that what we have done previously. So modifying the microstructure, we can see these trends, how it will affect the load carrying capacity, and in this case the creep is the most important deformation mechanism. So we will try to apply this for the creep, so to see how different microstructural features actually affect the performance of the material. So I think I'm end of my time. So that was in brief what we have done in this ACHIEF project. Thank you.
Thank you very much, Andrea and Tom. Really. Now, well, following the program, I will give the floor to, let's say, TOPAM project that is represented by Ulrich Krupp. He is mechanical engineering, has a mechanical engineering background, PhD and habilitation in materials engineering, focused material degradation by fatigue and corrosion by University of Michigan, postdoc in Philadelphia between 2006 and 2018, professor for engineering metallic materials at University of Osnabrück since 2018, and head of RWTH-AACHEN Steel Institute and coordinator of TOPAM project. So please, Ulrich, the floor is yours.
Okay, Fernando, thank you very much for this kind introduction. Well, so the dates were a little bit wrong, so I spent So between 2006 and 2018, I was in Osnabrück, and 2018 I started to at the Aachen Steel Institute, and maybe a few words more about the Steel Institute. That is a coordinating institution of the TOPAM. So we are about 100 employees, and we are covering the complete value chain in metallic materials engineering. So we start with computational materials engineering, and then we have facilities doing the casting, forging of laboratory melts, and then we analyze the microstructure and correlate the microstructures and we see properties, corrosion, fatigue, and also creep, as you will see later on in my presentation. So I would also acknowledge my co-workers, my institute. So in the project, we are quite a lot of people, so I'm not able really to mention all of them. Okay, let me start with a more general question. Is additive manufacturing sustainable? One can say, no, because it's an energy-intense powder production involved. So there's a rather limited recyclability of powder. And so we have usually many processing steps, and starting from the atomization, and often we have post-processing like hot isostatic pressing and so on. But nevertheless, I would say, the answer is yes. Additive manufacturing can be sustainable because we have the potential of a high functional integration. Think about titanium, then we can achieve a high material efficiency to have material only where it is needed, and the lot sizes of just one are possible. So that make it economically feasible and highly sustainable. A good example where it can be sustainable and that is where TOPAM, our project, comes into the game. These are gas burner heads in process engineering, and so these kind of gas burner heads are exposed to high temperature, aggressive environment, high gas flows, thermomechanical loading, reducing, oxidizing and environments. And so there is a high potential for improvements in terms increasing the service life, to optimize gas flow characteristics, and to increase the temperature, so that doing it by additive manufacturing, we may end up in a higher efficiency of process engineering steps. So these gas burner heads are operating at very high temperatures. So as we heard before, the temperatures go up to 1300 centigrade. And so that is an example of our new design of the oxygen tip of such a gas burner head. And what we're trying to do is to integrate sensors to get data from inside the process of temperature. So that can be done by additive manufacturing. High temperature stability then can be obtained by creep-resistant materials at these high temperatures, and different than the approaches that were introduced before. We are aiming at ODS materials, so oxide dispersed strengthened materials. Oxide dispersed strengthened means so we have to implement nano-sized precipitates, and they must be of very high thermal stability. So that means that they do not grow bigger during service at high temperature. And that is only possible either by strictly controlling walls as a chemical composition or by mixing hard oxides as a alloy powder wall. A typical, well, here you see an example of mechanically alloyed material, so mechanical alloying or hot, and in combination with hot extrusion, that is today the method to produce bulk ODS materials. Well, we are developing alternative approaches for additive manufacturing, and I will introduce this later on, but so that is a freeze granulation, high energy milling, and internal oxidation and nitridation. And while we are aiming at 3 different alloys, while a typical nickel-based superalloys, alloy 602 and 699, an iron, chromium, aluminum high temperature alloys, that is Cantal AM 100, and while for somewhat lower temperatures, while we work on alloy 400 as what Monel type alloy, which were shown in a preliminary study while to have a very excellent resistance to metal dusting. Well, to do this, in TOPAM, so we gather a large consortium of material producers like KME for the copper alloys, VDM, metals, Cantal, then for casting equipment and mechanical alloying, that's Indotherm or Sots, and several institutes doing also a lot of analytics like Dishima Research Institute, then University in Madrid, and many, many more. So that means we are able to represent the complete value chain in additive manufacturing, where we start with the computer-aided design, and then the data compilation and optimization then for additive manufacturing. So we have then the powder production by means of gas atomization, powder preparation. Well, here it includes the implementation of the oxide particles. And then actually additive manufacturing, here we are using laser powder bed fusion. And then finally, the component testing and so on. Well, let me start to introduce the gas atomization process. Here the alloy is molten in an induction furnace, and so then by high pressure argon, the melt is then sprayed into a large stainless steel vessel, and so the solidified droplets then become later on the powder that can be seen here. That is a high-speed camera. Here, so the atomization starts, and here you see the droplets which then solidify and then will become then the powder. Then the raw powder then has to be prepared by means of sieving, so the coarse powder particles, and then we use an air separation to get rid of the powder fines, and then so that is a suitable powder then for laser powder bed fusion. Next step is then laser powder bed fusion. Here we do a 2-dimensional laser melting of the powder bed. Then it's the next step. Then the build platform is then lowered, and by means here you can see it as a recoater is then applying new powders that you can see here in the video. And then so the process starts again, then with the laser melting, and so the component is then constructed by layer-wise laser melted. And so finally, you have to remove then the remaining powder, and so the part needs to be then removed then from the building platform. The main parameters then are the laser power, the velocity, layer thickness, hatch distance, and the absorption of the laser beam. And so that is a very dynamic process that then determines what is the microstructure of the material. So we see then so these EBSD plots and shows that we have some texture in with respect to the build direction. And that, of course, was this kind of anisotropy determines also the mechanical and technological properties of the material. Well, so we try to represent the process by a finite element modeling, so the temperature distribution during when the laser is then hatching across the substrate. From that, so we get the temperature time distribution, and that can be then used to model the resulting microstructure, while here the dendrite arm spacing by the phase field simulation micros, and that can be then used to reconstruct then the grain structure and size this distribution. Well, the next slide then shows a sketch of the whole ICME approach. Well, the ICME then stands for Integrated Computational Materials Engineering. And as mentioned already, so we are using then micros to get the microstructure. While there's a second flow where we predict the nanoparticle melt pool drifts to get our particles distribution. And so together we should be able to predict the mechanical properties, and then finally that will end up then in the predicting the performance, and that is also in TOPAM, the last work package, so the performance testing. Well, here you see a model that we are using to predict the creep rate, and that shows that the model works quite well. So for ODS bulk alloys, that is the non-ODS AM100 that we are going to optimize by ODS, so that we have a substantial decrease of the creep rate. And that can be so we are able to use then the computational thermodynamics, and we get the volume fraction and the particle size. While here we see an optimum that is somewhat below 10 nanometers. So that means we really need to have very small particles. Well, so we are using three ways in order to get the small particles in the material. So that one is a high energy milling of the ceramic material in combination then with a metallic powder. That shows one example where we have done this with an aluminum alloy here. So you see those small grains and then the nano-sized particles. So another way that we are exploring is an internal oxidation and nitridation by adjusting so the oxygen or nitrogen pressure in a fluidized bed system. Then we can obtain really then nanoscale alumina or, for instance, titanium nitride particles, and so they are staying then stable when they are applied to the operation environment in process engineering. Okay, next example is then so freeze granulation. So here we use the fine particles and from the air separation process, and so that is then processed together with a binder and water, and so we so the system is then frozen, and so we are spraying then the suspension, and then we get this kind of frozen droplets, and so inside it looks like this. So we have the small particles, and inside these are the oxides, and then after debinding, so we get so printable particles, so in the scale of about 50 micrometers, and they contain the fine particles and also the oxides. While here this test was then done with 3% yttria. Well, in the same direction, and so that was a very recent results from last week. So we were using a copper chromium zirconium alloy in combination with aluminum nanoparticles, and what here you can see was the nanoparticles on top of the atomized powder, and after laser powder bed fusion, what we really can find so particles inside walls, so they are of the size of about between 10 and 20 nanometers, and so they should be effective in improving the creep properties. And that is what. And finally, what I would like to show, so our characterization, so we are doing so the creep testing and so high temperature corrosion testing within so the consortium, while creep means while so right now we are able that our unmodified laser powder bed fusion alloys has this rather the same properties as bulk alloys, but also we see ODS, so we are aiming at much lower creep rates. While at the same time we have to achieve a high oxidation resistance that is then maintained in this case by the alloy 699XA by thin chromia scale. We have some internal oxidation, and so that is these are the two main characterization steps. So let me summarize this short overview about what we are doing here in TOPAM. AM or additive manufacturing can contribute to sustainability if we can improve the performance of individual components. That means that we need to develop AM-specific metal powder materials, and I hope I could show you a way how we can systematically use ICME guided materials design for additive manufacturing, and how it can be used for the demanding components that we have in process engineering to get to higher efficiency and longer life for applications under extreme conditions. And with that, I would like to thank you, and also mention that in the framework of TOPAM, so we are organizing summer schools, which is open to the community. If you're interested, just contact us, and with that, I'm it's the end of my presentation, and thank you all for listening.
Thank you very much, Ulrich. Very interesting presentation, really. Thank you. So we will go to the next panelist, the next presenter. We will continue with Thin Wave project. It's represented by Roberto D'Ambrosio. Roberto D'Ambrosio is a postdoc research fellow at the Institute for Chemical and Physical Processes of the National Research Council in Pisa. His research activities mainly focus on the production, study, and multiphysics modeling of silicon carbide-based ceramic matrix composites manufactured by microwave-assisted chemical vapor infiltration process. He actively supports the coordination of the Thin Wave project, and he is currently responsible for the microwave chemical vapor infiltration laboratory in Pisa, where he leads all the experimental activities rounded with the non-oxide ceramic matrix composites manufacturing chain and characterization. So, Roberto, the floor is yours.
Okay, thank you very much, Fernando, for the kind introduction, and good morning, everybody. So in the framework of this webinar, I will present you the Thin Wave project contribution with title Enabling the Potential of Ceramic Matrix Composites for Energy-Intensive Industries. I will present this work on behalf of the project coordinator, Professor Andrea Lazzari from the University of Pisa. So I will start by clarifying the project background and scopes, moving then to the experimental activities carried out and technologies employed. So as we know, the escalating problems resulting from climate change are getting advisedly exponential attention. This is reflected in the European Green Deal, which clearly outlines the mid and long-term objectives which need to be fulfilled in order to reach the carbon neutrality target by 2050. So in such context, research and innovation are directed in several directions, including the change of processes to get lower CO2 emissions, and this will require, among the others, novel material solutions to address the more fluctuating and harsh environments expected. For energy-intensive industries, where very high temperatures in controlled atmosphere have to be reached, the industries will need to follow one or more low-emission pathways. In particular, concerning the steel industry, the main tender will be to use energy inputs provided from circular carbon technologies, fossil fuels with carbon capture and storage, and clean power for hydrogen-based iron-making processes. So as an example, in steel processing lines, indirect heating of products is usually carried out by using radiant tubes equipped with gas-fired burners. These components are usually based on different grades of Inconel stainless steel, which, depending on the location, are exposed to severe thermal loads up to their temperature limit. However, due to the expected shift to renewable energy sources involving mixtures of hydrogen and biomethane up in the future to 100% in hydrogen content, novel materials will be required not only able to sustain these extreme conditions, but also phenomena like hydrogen embrittlement for metals or hydrothermal attack for ceramics. So in this framework, ceramic matrix composites could play an important role due to their high toughness, low density, high thermal stress resistance, and chemical inertness, which are making them increasingly attractive in a large palette of energy-intensive applications. These materials could be distinguished in oxide and non-oxide-based CMCs, depending on the main components, namely the fiber and the matrix, which could be based either on an oxide material as alumina or a non-oxide material as silicon carbide. However, due to the high raw materials and processing costs, CMCs are only employed in high-end areas. Therefore, in SEMWAVE, our first aim is to introduce an innovative microwave-assisted chemical vapor infiltration technology to manufacture CMCs. Moreover, the final goal of the project will be to validate a CMC prototype based on a joint oxide and non-oxide CMC tube to be tested in the relevant environments of interest for future radiant tube furnaces in steel industries. Moreover, as a part of the project activities, a series of tasks will be carried out to investigate more enabling technologies to favor a wider application of these materials in additional sectors. So in order to reach all these goals, the SEMWAVE Consortium gathers a team of 13 partners among academics and industries, joining all the relevant expertise in all the project fields. So I will start now by going more in detail into the microwave CVI technology. Let's start by saying that commonly CMCs are fabricated by infiltration methods. Among those techniques, the chemical vapor infiltration, or CVI, is one of the most preferred, since it allows to obtain the highest quality matrix in terms of resulting thermomechanical properties. Specifically in this process, a gaseous ceramic precursor infiltrates a porous fiber structure and reacts at high temperature on the fiber surface, depositing a ceramic layer. However, in conventional isothermal isobaric CVI, high vacuum levels are needed to favor the penetration of the reactive gases inside the preform, leading to a strong depression of reaction kinetics with resulting processing times also of several weeks to achieve the final density. So one of the solutions to overcome the low deposition rates observed in conventional CVI is through the application of thermal gradients within the preform. In this framework, the usage of a microwave-assisted heating is therefore an attractive alternative due to the peculiar volumetric heating mechanism, which, coupled with surface heat losses, results in an inverse temperature profile in the sample. In this way, the infiltration can start from the heart of the preform, moving towards the external surface as the density of the material increases. So in this way, the premature pore occlusion due to crusting can thus be completely avoided, resulting in a reduction of about 1 order of magnitude in the processing times. Nevertheless, the application of a microwave heating leads to additional challenges for the effective processing of materials. Among them, the two main challenges regard the non-uniform heating due to the formation of standing waves inside the cavity with the resulting heterogeneous heating, and the control and optimization in operando of the microwave heating parameters, which needs to be finely tuned with the material properties change during the process. Indeed, although the most convenient from the economical point of view, the oldest microwave magnetron sources are prone to several drawbacks, which are mostly related to the incoherent nature of their electromagnetic emission, which cannot be controlled in phase and frequency, resulting in very narrow frequency emission values. Differently, with the newest microwave solid-state sources, both the forward and reflected power levels can be easily adapted into the whole frequency band of interest, with the further possibility to implement closed-loop controls in order to automate the whole infiltration process in our case. Therefore, one of the main advancements in the framework of the SEMWay project has been the design, development, and integration of these new microwave solid-state sources to our microwave CVI plants. As an example, a first ever developed prototype able to deliver a total of 6 kilowatt of microwave power to our reactor has been developed by our partner Frikun Malla. Here, I'm showing you a panoramic of the microwave CVI plants with the solid-state sources highlighted, which have been integrated to our systems, and will be respectively dedicated to the manufacturing of non-oxide-based CMCs and oxide-based CMCs. Another major advantage coming from the application of this new technology it derives from the solution of the coupled electromagnetic thermal problem by a rigorous numerical modeling, which has been carried out by the Institute of Physico-Chemical Properties in Pisa. In this way, the most efficient operational conditions can be identified in terms of the resulting operating frequencies, which have been chosen following three different criteria, which are the achievement of the highest energy efficiency in terms of energy deposited in the sample, the selection of modes with electromagnetic field distribution suitable for the application of interest, and the minimized cross-coupling level in terms of reflection of power in the other channels, which is inevitable when working with more than one source at the same time. The main outcome of the modeling will be, of course, the temperature profile in the sample region as a function of the electromagnetic field frequency, which has been determined looking for two main targets, which were the improvement of the heating uniformity to favor a wider densification of the material, and secondly, the tailoring of the necessary temperature gradients to achieve the characteristic inside-out densification of our CMCs. Of course, another major task regards the preparation of the CMC preforms for the microwave CVI processes. So a specific process chain has been developed for both categories of material at the Fraunhofer Institute of Bayreuth, developing CNC preforms which were based on uniformly coated fibers and with selected preform geometries with an adjusted open porosity to favor the penetration of the reactive gases during infiltration. The first step involved the interface coating of the ceramic fibers, which has been done in a roll-to-roll process by a wet chemical route, achieving in this way very uniform coating of the ceramic fibers in a short time span and continuously. The interface is a very crucial component for a CMC material, since by controlling the bonding strength between the fiber and the matrix through the interposition of this layer, it is possible to activate a series of toughening mechanisms under stress, resulting in its characteristic pseudoductile fracture behavior. And here I'm showing you the coating systems which have been employed for both categories of materials. Following the next step regarding the coated fibers which have been impregnated, passing them through a bath with a ceramic slurry. and wounding them on a specific core depending on the final geometry, which has been done by filament winding technique. Why this technique? Because at first it allows a very fine adjustment of the fiber reinforcing architecture, and secondly, because it is not easy to handle stiff ceramic fiber rovings as our coated ceramic fibers. So once optimized the textile processing parameters, the preforms have been thoroughly dried and thermally treated to remove them from the cores, obtaining the final geometries here displayed, which had a tubular and a plate-shaped geometries for both categories of materials. Coming now to the microwave heating and infiltration processes trial, these activities are being carried out in these months. The first results obtained from microwave heating trials immediately showed very interesting results by using the latest solid-state sources previously described. These trials have been carried out monitoring the temperature profile evolution on a typical 6-6 sample after 5 minutes and by a single port excitation. So as you can see, by finely selecting the operating frequency, we have been able to selectively heat specific sample regions covering from 30 to 50% of the whole material surface. But look what happened when we combine these three conditions by using a multi-port multi-frequency approach. You can see that in this way, the heated surface of the material rises to about 70 to 80%. Whereas we just could heat and infiltrate later the material by looking for a different operating frequency, aiming at the end, of course, to the full infiltration of our materials. As for the oxide-oxide materials, I present you the first results derived from microwave CVI deposition trials, which have been successfully carried out at the University of Birmingham, depositing the desired alumina matrix. Currently, optimization works are being dedicated in order to maximize the deposition rates while being able to improve the quality of the alumina matrix desired. Another crucial activity regarded the multi-physics, multi-scale model of the microwave CVI processes, which have been carried out at CNRS in Bordeaux. Here, it is depicted the modeling strategy, which covered 3 different scales, from the intra-fiber bundle scale of tens of micron up to the whole part scale. You can see that in order to model the microwave CVI process, we need to solve the conservation equations for 4 different physical problems. And also, we need to know the laws providing the change of the geometrical and transfer properties during the infiltration process. So the first task dealt with the collection of a series of image data coming from X-ray computerized tomographic scans and SEM micrographs, which have been then processed by specific tools in order to detect the precise fiber reinforcement architecture. So once obtained our elementary computational domains, the physical properties have been determined in order to retrieve the effective bundle coefficients as a function of the local fiber density and infiltration degree. Here, I wanted to show you first results from macroscale simulations, which shows the porosity evolution when applied a fixed thermal gradient in this case, which is a quite simple one-dimensional case representing a single pore channel. What appears immediately, confirming the importance of controlling the temperature gradient throughout the preform, is what Professor Vignolz defined as the Trilby hat effect, which means that at the beginning we start from a good thermal gradient, but after a few iterations, the deposition stopped in the hottest part. So we couldn't reach the decrease of the porosity up to 0 value as we desired, since the gas get depleted. And this is something that we would like to quantify in the framework of the project, since it could be avoided by precise numerical modeling. So I spoke to you at the beginning about also a series of activities regarding research on the more enabling technology to favor a wider application of CMCs. Among them, if the issues, for example, related to joining CMCs to themselves, but also to other materials could be solved, these materials will be employed much more efficiently to obtain also complex hybrid structure, complementing with unique properties their final behavior, and so to be applied not only in the steelmaking sector, which is our use case, but also in other energy-intensive sectors. So in order to reach these goals, joining materials with suitable compositions have been developed, which were based on brazing alloys and glass ceramics, paying special attention to pressureless joining technologies in order to guarantee the achievement of industry-friendly solutions. As you can see, both these glass ceramics and brazing alloys compositions have been optimized, selecting them in order to guarantee higher temperature softening points based on the operating conditions expected, but also a high wettability and comparable coefficient of thermal expansion. As you can see from the comparison of the failure surfaces, a very good adhesion was obtained for both solutions applied, which have been tested on actual CMC substrates, so both oxide and non-oxide based materials. Furthermore, as for the oxide-oxide joining material candidates, they've been also validated in post-combustion environment, thus simulating the real operating conditions in two different sets of parameters, which are depicted in the orange box below. As you can see, the joints withstood quite well the flame tests with no mass and microstructure evolution during the process. Another important complementary activity regarding the surface modification of the CMCs, since we wanted also to further improve the joint strength by favoring a mechanical interlocking of the joining materials with the underlying CMC substrate. And this activity has been also flanked by numerical modeling activities. Finally, the last task of which I wanted to speak to you about regarding the design of specific environmental barrier coatings in order to enhance the lifetime of the materials by improving their corrosion resistance. So two different environmental barrier coatings systems have been developed, adjusting the rheological properties and the coefficient of thermal expansion to have a good match with the underlying CMCs produced. Both of those systems were based on multi-layer system with one bond and one top coat, where the bond coat was based on either mullite or zirconium titanate systems, while the top coat was instead based on rare earth silicates. So coming to the conclusion, in the framework of the same wave, our main aim was to make more affordable the application of CMCs for energy-intensive industries. So we focused on a series of challenges involving cleaner and more efficient preforms manufacturing technologies and infiltration processes, up to a series of technologies to further optimize their properties and have a wider application of these materials. In the next steps, we will focus to the optimization and production of both non-oxide and oxide-based CMCs, which will be characterized in terms of their thermomechanical and corrosion properties, to be finally validated using the joining and coating material candidates developed and described before in a specific pilot plant, which is being developed in the ArcelorMittal facilities in Spain. If you are interested in further updates, I kindly invite you also to follow our updates on the project website. And I would like to quickly thank all the consortium partners for their work and support in the preparation of this presentation. And of course, also all of you for your kind attention. Thank you very much.
Thank you very much, Roberto. It's been a very good presentation, really.
Thank
Okay,
you.
so we'll go ahead with the next project and next presenters. Next project is Compass CO2, and it will be presented by two persons. First one is Canma. Dr. Canma did his PhD in CIAP in France, and now is postdoctoral research fellow at the School of Metallurgy and Materials in University of Birmingham in the group of Dr. Sandy Wolfs. His main focus is on the development of novel chromium-based superalloy for concentrated solar power, from the alloy design, manufacturing, property evaluation, and microstructural characterization. He has rich experience in microstructural characterization using electron microscopy and atom-prof tomography. And the second presenter is Matthias Gallets. Associate Professor Matthias Gallets is Division Head of Materials and Corrosion at the SHEMA Forschungs Institute. He is co-author of more than 150 papers in the field of high temperature corrosion and coating. So, Canma, you've got the floor, please. Go ahead.
Can you see the screen?
Yes, perfect.
Yeah, thank you for the introduction. And good morning, everyone. Happy to be here with Matthias to present some of the work ongoing with work package 3 in the Compass CO2 project. And the topic today is the novel chromium-based alloy strengthened by intermetallics for structural and coating applications. And I would like to acknowledge first our partners within the work package, which give a lot of support on this work. And in this presentation, there are 3 parts. So first, I will start with the introduction to the project and the concentrated solar power, CSP, and chromium-based alloy, followed with 2 different parts of two different chromium-based material. So first comes a brief introduction to our project. The Compass, in fact, the concentrated solar power plant transfer the solar energy to thermal energy to produce electricity. And the advanced CSP aims at integrating a hot particle system as primary cycle into a supercritical carbon dioxide Brayton cycle as a secondary cycle to produce electricity. And in this case, we can improve the temperature of the whole system to push the boundary of the thermal efficiency and optimize the economic benefits. And in the Compass CO2 project, in the work package 3, we have focused on the development of metals for the heat exchanger tubes. In fact, the heat exchanger is the interface of the hard particle and the supercritical CO2. So which this design creates a lot of challenge on the structural material of the heat exchanger tube. For example, it need to have high strength at high temperature, and it need to be resistant to corrosion and oxidation, and also it need to be resistant to erosion to particles, and also it will operate at high pressure for a long time. And as you have seen, a lot of advanced material mentioned in previous presentation, including nickel superalloy, austenitic steels, ferritic steels, and some ODS steels. And in Compass CO2 project, we have suggested also another alternative to this conventional material, which is chromium-based alloy. And why chromium? If we look at its properties, its advantage is quite obvious. It has a high melting point, 400-500 higher than nickel and iron. It has a low price, and it has good oxidation resistance and also good thermal conductivity, which is critical for heat exchanger. But its drawbacks is also quite obvious. Its lack of strength need to be strengthened. It is brittle at room temperature and has some embrittlement, nitrogen embrittlement at very high temperatures. So to strengthen chromium, in our project, we use some intermetallic precipitate to achieve this goal. And to strengthen this, we have used 2 approaches. The first approach we use is to strengthen it with a coherent BCC ordered intermetallic phase from the BCC prime microstructure mirroring to the gamma prime microstructure in the nickel-based superalloy for high temperature application. And in fact, this forms so-called BCC superalloy. This concept has been adopted in other BCC metal like tungsten, beta titanium, and also BCC iron, and they achieve quite an improvement in this material. And the second approach is to introduce the A15 phase, the chromium-3 silicon into chromium to pursue both strengthening and also improve the oxidation resistance and nitrogen resistance. So in the following, I will present the first part for the development of novel chromium nickel aluminide BCC superalloy. And in fact, the design of this alloy is instructed by the phase diagram calculation. As you can see in this ternary phase diagram, we have a single phase chromium area and a single phase B2 nickel aluminide ordered BCC phase, and with a dual phase intermediate. So if we draw the vertical section of this line, and we can obtain this pseudo binary phase diagram of chromium and the nickel aluminide, and the form of this phase diagram enables a quite classic superalloy design, which means we can heat treat the sample at high temperature to achieve a single phase area, then to another lower temperature heat treatment to precipitate out all the precipitate which strengthen the material. And experimentally, we have demonstrated that this BCC superalloy design works in chromium with the chromium matrix and nickel aluminide precipitate. But the issue is that, as you can see, the area of the single phase is quite small. And what's more, that means if we add more a high content of nickel and aluminum, we form this grain boundary precipitate or dendritic microstructure, which is they are detrimental for the ductility. And what's more, the CAFA database of chromium-rich area is in fact need further investigation because they overestimate the single phase area. That means we cannot we cannot add as much as predicted nickel and alumina. It limits the volume fraction of the precipitate that we can create in a material, so limit the strengthening. So the first step is to seek a way to increase the solubility of nickel and aluminum. And the one way we instructed by the calculation is that we can add iron. So here we show in black line the phase diagram with 0 iron, so without iron, and with 10% atomic percent iron and 20% atomic iron. And we can see the solubility limit. So the single phase area expands to the right, so has a larger area, which so it's supposed to increase the solubility. And experimentally, as we can see from these two micrographs, from this point with iron and without iron, here we form the dendritic microstructure. But if we add iron, we form a quite homogenized single phase microstructure with this beautiful large grain. And also, if we do in these two materials, when we do a lower temperature aging, we obtain this precipitate microstructure, and in the quaternary. So with iron, we have a higher volume area fraction in our material, which enhances the strengthening of the material. And after obtaining this precipitate A2B2 microstructure, we are interested in characterizing this microstructure. So what's the structure of the precipitate and what's their interface? And due to the limited time, I will just show some key results of a benchmark alloy. So nickel 5 chromium, 5 nickel 5 aluminum, 10 iron. As we can see from the micrograph, we have this in most of the material. We have nanoscale spherical precipitate with a cube-to-cube coherent orientation to the matrix from this TM diffraction pattern. And also, in fact, this novel material, as chromium, is quite a nascent class of material, and this material has a wide appeal for the community, and so we have created a wide collaboration with other external partners. For example, we have performed high-resolution TM observation on the interface, which shows by this micrograph, and show the interface is highly coherent between the precipitate and the matrix. And also, we have performed this observation was performed at EPSIC in Diamond. It's a microscope center, and we also did synchrotron powder diffraction in Diamond on beamline 11 to measure lattice parameter of the two-phase B2, the precipitate B2 phase and the matrix phase, to determine their lattice misfit, which is a quite critical parameter for the this BCC for the superalloy design. And the lattice misfit was determined to about 0.1%, a very low level, similar to the chromium nickel superalloy, which is important results, important design factor in this system. We also done atom probe tomography studies through NUF skin with the atom probe group in University of Oxford to study the distribution of elements in different in precipitating matrix and also potential segregation at the interface. So after characterizing this microstructure, we are interested in to know what's their property at high temperature. So the first thing is whether the temperature, what's the coarsening rate. So whether they are stable, these precipitate are stable at high temperature, and whether they coarse a lot. So we have performed different aging at different temperature for different times, study the coarsening kinetics of this material. And we can see the evolution of the volume of the precipitates at different temperature in function of the aging time. And then we can determine their coarsening rate. And it's found that their coarsening mechanism is diffusion controlled. And also, if we compare with the other common superalloy, cobalt and nickel FC superalloy, the coarsening rate of the precipitates in chromium is much lower than the other superalloy, which demonstrate quite good thermal stability of this material at high temperature. And with this experimental result, we can also deduce the interface energy. And there are some experiment work and there are some simulation work ongoing with our partner VTT to validate this interface energy measurement as well. So finally, we are interested in also the strength of this material at high temperature, and we use the compression rig, high temperature compression rig developed in Matthias Group in Denmark. We compress this cylinder to have a strength-stress curve and determine the yield strength of material at different temperature. And here we show some results at room temperature and temperature higher than 800 degrees. You can see the quaternary alloy chromium BCC superalloy has provided high strength at both room temperature and temperature higher than 800 degrees, which is the temperature for end-up application. So finally, for this class of material, there are some brief conclusion is that the solubility of nickel aluminide is quite low in chromium and it needs improvement. And also there's some uncertainty in the CAFA database, which need to be improved to better predict the phase diagram. And also adding iron can increase the nickel and aluminum solubility, which enable a homogenized microstructure and the tailoring of the volume fraction of the precipitate, which expands the design space of the material. And also we have identified a good thermal stability of these precipitates in BCC chromium BCC superalloy, and these all provide a good strength for the high end application temperature range. And in the future, there are a lot of work foreseen within the Compass CO2 project, including the environmental behavior investigation, the oxidation and the CO2 corrosion test, also creep test with small punch enzima. And also our partner VTT is also on doing modeling work on the CAFA, post CAFA and deformation behavior. And also we will investigate the possibility to transfer this bulk material into a coating technology. And then I will let Matthias to present the other part of the work.
Yes, thank you, Khan. Hello, everybody. Welcome also from my side. You already got an introduction on the chromium-based alloys. Now we change the system a little bit and look at systems that are silicon alloyed instead of the aluminum nickel alloyed systems. The big advantage usually is that we form for those systems, as you will see in a second, a duplex scale of chromia and silica that strongly improves the oxidation resistance and make those systems interesting for not only oxidizing but also carburization. at high temperatures. Also, what we have when we add silicon are so-called A15 structured phases. As you can see here on the right side, you see the silicon and the chromium. It's an intermetallic phase, and these hard particles should be very good for the erosion properties that we expected in the particle CSP plant. Okay, next slide, please. So this alloying silicon, as I said, has this huge advantage that, as you can see here, pure chromium is basically not usable above around 900 degrees C due to strong nitridation that is taking place, also strong spallation. There are high growth stresses in pure chromium. But when you add only 3% of silicon, as you can see, we change to a parabolic behavior with much, much lower weight gain. And if you add silicon, all of a sudden we come into ranges that basically no alloys, no commercial alloys can reach at the moment. At 1200, it's also strength-wise, it's a limit, of course, for nickel-based alloys. So this makes those systems very, very interesting. As you can see here on the right side, especially nitridation. This is the nitrogen, the N signal. There's very, very low, and this is usually the biggest problem for chromium-based systems at high temperature. This is the reason why it was abandoned in the 40s, 50s of the last century. All the chromium research basically stopped back then for high temperatures because of this issue. And now with silicon, you can all of a sudden suppress this. So that's why research took off again in around 2010. And now a lot is going on with chromium systems again, since you have methods to suppress this nitridation. Okay, let's go to the next slide. Here you can see the heat treatment at 1200. We have a single phase oversaturated as-cast microstructure. This is from alloy development, arc melted sample. And then when you do a heat treatment, for example, at 100 hours, 1200 degrees C for 100 hours, then you can see that you find small precipitates of this A15 phase. And they not only increase the creep resistance, which is beyond this talk, but you can see on the right side that it strongly increases the hardness. This is the Wicker hardness at room temperatures, and we compare it to two commercial alloys, the Inconel 740, which is a high nickel-based alloy, basically really a high end of those that can be manufactured as tubes or for this receiver material or heat exchanger materials. And then we have a Sunicro 25, which is also a high strength iron-based alloy still. The upper end that can operate up to 700 degrees C. And you can see that when we have our 8% silicon alloy, which is the eutectic alloy with about 40% of those precipitates, the hardness goes up strongly, and this makes it interesting for erosion properties and those contacts with the particles. The issue there with those alloys, as was mentioned already as well by Khan, is the DBTT, ductile to brittle transition temperature. So the issue is that here you can see also samples from these compression tests that have been introduced already. From the left to right, the temperature changes up to 700 degrees C, and at 700, all of a sudden we get nice compression without cracking, but everything below basically cracks. So we tried also improvements that were promising from the literature by alloying with iron and nickel, but so far we couldn't significantly decrease this ductile to brittle transition temperature. And literally it's a make or break criteria for structural applications. So we went another way to apply this as a coating, which is then shown here. The slurry coating technique is a technique that has been around for years for aluminum systems. It's also commercialized and used a lot in the turbine sector, for example, but also in the chemical process engineering. It's applied on large components like tubes. So here for chromium, the issue is that the melting point of chromium is way, way higher than that of aluminum. And so we had to find ways to get around it, to make this possible as a slurry coating at a, let's say, adequate heat treatment. So it needs a binder removal at around 350, and then the second heat treatment is still pretty high in the range of 1150 to 1200 degrees C for around 6 hours. But then, for example, on nickel-based alloys, it's still in a range where we can heat treat, and then we have nice coatings, as you will see on the next slide. So here we have two micrographs, one on a Sunicro 25. So also this steel is still possible to be heat treated at those temperatures. And as you can see on the right side, we find a high chromium rich phase without many cracks. We have a few pores and a few, it's mainly silicon, actually those round shaped pores, internal silicon oxidation during the process. But then in general, we have these very, very high hardness, as you can see on the right, and also this highly improved, what we expect, highly improved oxidation resistance. The same is true then below for a Inconel 740 alloy. Here you can see that we have much more nickel in our outer coating due to the fact that we have also a nickel-based alloy here. Also, we have to add a little bit of nickel to our slurry. So we form not only the A15 phase, we also form a chromium nickel silicon intermetallic phase, but still we achieve this goal of this hard outer layer without cracks. And you have to keep in mind that this was cooled down already from an extremely high temperature of above 1100 and doesn't form cracks. So the CTE, which is also of concern usually of those systems, the thermal expansion coefficient, is not an issue. And this shows that probably also during the application temperature of around 800 degrees, that should not crack. Okay, the next slide, please. Then I already come to the conclusions. I mean, we have limited time here to show all projects, but I wanted to show you that the chromium silicon alloys really have a high potential for high temperature applications. At the moment, we are still struggling with the ductile to brittle transition temperatures. As you can see here, it looks a little bit like a ship that is falling apart here in space. So the way to go, and this is the way, is the spraying technology of a slurry coating and then a heat treatment. As you can see on the right-hand side, when you do slurry spraying, you need a lot of protective equipment to do that. But then we think we found a way to really apply these coatings on state-of-the-art materials that then can be used as the heat exchanger material for the particle CSP plants that are developed in Compass CO2. Yeah, with that, that's my last slide. I would like to thank all our project partners. Especially, I would like to thank also my PhD student, Michael Kerbstadt, who is on vacation actually at the moment, and also Emma White for her contribution from our team. And then the rest, as you can see here on the left side, we have a lot of contributors. And I'm running out of time if I would mention all of them, but I'm grateful for their support. Yeah. Thank you.
Okay, thank you very much, Can and Matthias. Well, and I will continue. We have a slight delay, but I think that, well, in the program, it was forecasted only 10 minutes. That's not like this. Albise, you will have 20 minutes as everyone. So there's a small gap in the program. So I will present the next project that will be the last one is FORCE. It will be presented by Albise Bianchini. He's since 14 years, Albise Bianchini works as project manager in the Material and Process Development Unit of MBN, Nanomaterialia. His background is on material science with a special focus now on materials for the energy sector and methods for material powder production via chemical alloy. So the floor is yours and you can go ahead, please. You are muted, Albise. Yes, we are still muted. We see the... I will check. We can hear you. One moment, I will try to.
Okay, I think I've done it.
Now, yeah, it's okay. Now it's
Sorry.
okay. Yes, you can share your screen, please.
Good. Okay, it should be working now.
Yes, it's fine. Well, yes, it's fine.
Perfect. So, Forge is a project that is about material development for energy-intensive industries. In the consortium, we have quite a spread distribution of entities from basic research up to industries that will eventually test out our materials. And this is needed because in the Forge project, we are trying to develop these new materials from the very first principles. Nevertheless, we are trying to apply them to the industry and validate them in real case scenarios. In the project website, when you see this icon in the slides, you will find more information about the theme of that slide. And yeah, so as the other projects, also Forge is focused on energy intensive industries, with the idea that with more performing materials, there will be the possibility eventually to save on energy efficiency, reduce in CO2 emission, and related to that, increase the lifetime of the components. In Forge, we are focused on specific industrial cases to guide our material development. In the cement industry, there is a lot of waste recovery and CO capture that is want to be improved, but there are high temperatures, high acidic contaminants, and abrasive particles that prevent the use of some materials, and in any case, have the premature erosion of the components used in that part of the plant. So for this scenario, we identified as a performance targets resistance to corrosion and wear. Similarly, in steel industries, the possible change to other fueling and chemical processes, alternative process chemistries for reduction of the ore make an interesting there is an intrinsic opportunity that is somehow prevented by problems related to hydrogen embrittlement of pipeworks and heat exchangers. And yeah, the performance targets here is resistance to embrittlement and wear. In aluminum industries, we are focused in extending the lifetime of extrusion dies because higher performance alloys containing silicon are sought. In the ceramic industries, the possibility to increase temperature of the kiln is prevented by thermal breakdown of kiln bricks. And this also complete our scenario of performance targets that we are looking into the project, that are corrosion resistant, hydrogen embrittlement, mechanical damage by erosion, and thermal breakdown that can be on ceramic components, but also alloys. And this identify basically our space of investigation, in which we have materials, different performance targets, and different manufacturing processes. In particular, we are focusing on 4 manufacturing processes that are related to the manufacturing of coatings, so HVAF, HVOF, cold gas spraying, laser cladding, and the 4 performance targets identified before. The idea of the project is to explore the space in order to find the possible combination of materials and processes that satisfy the performance targets for the different use cases. So at the end, we will end up not only with a specific solution from the material and process point of view, but also with a knowledge base of methodologies and data sets that will help us replicating this experience and for other sectors or for other performance targets. So this is the core idea of the Forge. It's a quite complex approach, and in Forge we are somehow embracing these complexities because we are not looking into classic metals and conventional metal alloys in which we can have some, we have a primary element and then substitutional elements or interstitial elements. But we are looking into compositionally complex alloys that have a much broader definition. There is no dominant elements. More than 4 elements are present with concentration from 5 to 40 atomic percent. And more than one phase can be present. This can give some benefits. We are using the composition and complex alloys as the framework for the high configurational entropy that can have unique, can provide unique mechanical properties, but also good corrosion resistance, and the possibility to tailor new combination of materials and be more flexible on the specific uses of the materials. In order to identify a good composition and complex alloy, we need to constrain ourselves to some elements to be included in this scenario. And in Forge, we identify these elements, removing out those that are less usable or not so really worth to considering at the moment. But also with this small group material, it's difficult to have a complete and systematic development approach. Can be an impossible task for a number of countless compositions, as we have seen also in other presentation. So the Forge approach is to be supported by deep learning algorithm, able to correlate the properties of the compositional complex alloys and the composition. So this can be done starting with an input data set, developing the algorithm that gives a prediction, and this prediction has to be validated against an experimental campaign that will provide eventually an output data set. This needs to be reiterated to further refine the algorithm output. So clearly, the starting point for this exercise is somehow data from open repositories and data from other experiences that are in the literature for high entropy alloys, compositionally complex alloys. And from this, we can get information on composition, sometimes in composition information on the phase measured, and something related to the production methods, and most importantly, the performance that we are looking into, in this case, hardness. These data have been integrated with data coming from physical modeling methods in order to provide to the data set more complete information on the specific composition, and also integration with other parameters calculated directly from the composition. So we had to use CalFAD connected with the Python systems in order to provide for a huge data set information of this type. This information has been used to obtain a correlation matrix that is able to identify which are the information that are more related with, in this case, the hardness value. So given this input vector, this is the starting point for the deep learning that with training data can do some prediction of the model. The system that we are using in Forge gives also the possibility to relate back to which is the most contributing factor to the specific property. So in the case of hardness, we can relate which is the most contributing factor for the specific hardness of this alloy. But we cannot stop here. So after the first loop of activities on developing this deep learning algorithm, we checked the system by induction melting and then a second iteration by physical vapor deposition to eventually arrive to coatings obtained on real components. We use this approach because the first iteration is helpful in assessing the algorithm and that we are going in a good path. The physical vapor deposition allow us to get more data points around the main composition that we are interested in. And then the last step is the one closer to the application. The information gathered at this stage will be directly related to the possible application of similar materials with similar techniques, but to other use cases. So focusing a bit more on these three steps, this part of induction melting have been conducted and has been very useful in assessing that the prediction of the deep learning, the machine learning algorithm was quite good, at least in terms of trends between the composition that we choose to synthesize by induction melting and the prediction that led us to this synthesis. There are a lot of problems related to the synthesis of these alloys that are completely new. But from this set of materials, we could have characterize them for hardness, corrosion, and also hydrogen uptake. So based on that, the machine learning has been refined, and more specific material libraries with a smaller subset of elements have been obtained. This technique allows to basically using gradients from the different targets of the PVD. This allows to have different points in the deposited wafers that have slightly different composition. We had to develop dedicated physics models that can maximize the congruity between the physics from in the PVD and those from in the bike. Otherwise, there could have been some incompatibilities with the final system, but this system has been very useful in providing a base for the data set to grow further in the deep learning. The last step was the mechanical alloying and the production of the feedstock material for the thermal spray techniques. So we choose for mechanical alloying because it's somehow more flexible in the production of new systems. Don't have to rely on fusion with different melting points. So it's more, and the output is also quite directly usable in the thermal spray sector. So here become a bit more clear also my involvement in this speech since MBN, the company in which I'm working, is focused on mechanical alloying at industrial level. It's a small company, and we are bringing this technology to different outputs from lab scale to industrial scale. Mechanical alloying works by basically a combination of fracturing, cold welding, heating locally the particles during the process, and this allows many different combination of effects. The creation of nano and microstructure, the performing of non-equilibrium metallurgy, dispersion of oxides in metals. And we have then the possibility to refine the powder output for the different thermal spray processes. Here are some examples of structures that can be obtained, that has been obtained in the past, not only related to forge, but in general with this technique. And the possibility that we have is to work with base metal that are iron, nickel, titanium, copper, or aluminum. This means that the same thing that we can do on iron-based system can be done also on these other systems. Our role in Forge is exactly this one. So starting from this composition on the left, that are those popping up from the different steps described before. There is this mechanical alloying phase that deliver a feedstock for trials on thermal spray coatings. This can be different particle size distribution according with the technique utilized for spraying. And we are now in the stage in which we are actually getting information from the coatings, assessing which is the best in parameters for thermal spray process. That is another layer of uncertainties that or complexity that is related with this kind of development. By having this kind of trials on thermal spray, we are gathering samples at different process conditions that are being tested for the performance targets that I was describing before. In particular, these are tested for wear, and these are also the input, the final input data set for the deep learning algorithm that should be able eventually to provide useful information also for other systems, other material systems, and other application scenarios. We are testing these coatings also for hydrogen embrittlement, corrosion, and thermal breakdown. And all these data contributes eventually to this knowledge-based system framework. So conclusion, but also somehow messages. We have seen that developing new materials requires combination of different approaches, not only deep learning processes. The creation of a data set for these algorithms has to be based on experimental data set in order to be more consistent with the final outcome. Once the experimental framework is identified, physics-based models can help improving the consistency of the data and even more improving the quantity of the data along with the experimental one. The compositionally complex alloy confirms the high potential in delivering outstanding performances, but there is a lot of challenges related to their assessment. And with this, I've concluded.
Okay, thank you very much, Alvise. I think that we have finished with your presentation. Now we will take a look at the questions and answers. There are no specific questions open at this point. So if anybody wants to make any question from the attendees, they can carry out any question. If not, well, this meeting is being recorded, and we will manage to give information to the register people where it could be found and how they could reach to this information. From my side, yes, only to thank a lot to the panelists, to the presenters for the effort that they have made to prepare the presentations and to be in this meeting. And also I expect that the attendees have had the pleasure to in my case, it's been very interesting, very exciting to know more about other different type of materials. So thank you very much to all of you, and just wait to have good results from this project in the future.